Good day once again, and we meet yet again. By the way, I know that you are still working hard on those exams. Let me just emphasize that for those of you that still have been asking questions about tutoring, please just hit me up on my email address and I'll pin it down below. That's info@mlungisinkosi.co.za. And by the way, for some of you who haven't subscribed, you can do so. All right. Please just tell all your friends, all of your friends and your family members who are doing physics that we are producing great content that can help you to pass those exams with an A. All right. Now, I just picked up a question on work, energy, and power. And once again, it's from the 2016 paper. That's the Gauteng paper in South Africa. But it will help you whichever exams that you may be writing. This paper will definitely help you. So let's just revise again on work energy principles. Right, so they say we've got a car that has a mass of 700 kilograms on a rough inclined plane. So I want you to note, and the moment they tell us that it's a rough inclined, rough just tells us there's frictional force, right? As shown in the diagram there. Okay, there's our car. And then they say, what is the net work done on the car if it moves up the incline at a constant velocity? Now, please, I want you to note, the moment we start talking about a constant velocity, there are several things that we can note there. First of all, it tells us that the acceleration is zero. Okay, if you think about Newton's laws, so it tells us acceleration is zero. And then secondly, what it does, remember that net work done is related to the net force, isn't it? So if the net force would be, if the acceleration is zero, it means net force is zero. And if net force is zero, it means that the net work done should also be zero. Okay, so there's no calculation needed there. So please just remember that for future questions when they actually tell you about constant velocity. Right, now secondly, they said to us, draw a labeled free body diagram showing all forces acting on the car as it moves up the inclined plane. Right, now let's talk about those forces. So first of all, I'm going to have, okay, remember they said it's just moving up the incline, so I know that I would have gravitational force. Okay, and note it's acting vertically downwards. Okay, I'm just going to make an adjustment where I'm writing just now. Okay, so we've made just a little bit of an adjustment there. So now, so something I didn't like about this question is that they did not actually state whether, the engine of the car does apply a force or not, but I want you to always note, you should take a cue from the mark allocation that's given. It will always kind of tell you how many forces you need to have. I can see this is 4 marks, so it means that the examiner assumes that obviously the car's engine was did exert a force. So I'm just going to say this is the force of the engine, or you can say this is the force applied if you want to. Okay, and I've got gravitational force there. Now note that gravitational force is acting vertically downwards, right? And then remember, friction opposes motion. So in this case, I know they told me it's a rough horizontal surface, so it's going to be my frictional force there. Okay, so by the way, for those of you who are writing in South Africa, please just note that when they ask you for a labeled free body diagram, you are actually supposed to give the words in full there, friction and applied force and all of that. Otherwise, if you use acronyms, so if you say this is FG or W, please just always just state there W stands for weight. Okay, if you call friction FF for argument's sake, just state FF is okay, the frictional force, right? And then please note we've got the normal force. Now ladies and gents, if you really have not watched my videos on work energy principles, please do so now. Okay, and they will help you to understand these sections. Now please note that the gravitational force as well as the normal force do not actually form one straight line. Okay, so just be careful of that when you do that. Alternatively, okay, which I'm just going to show you now, how we could have drawn that free body diagram. Now you can see we've got four forces. How we could have drawn that free body diagram is that we could have had the normal force, we could have had the applied force. Okay, please, I'm not going to write them out in full this time. We've got the frictional force, which is kinetic friction. And now instead of gravitational force, because that gravitational force in this case would not, you can see it's kind of a, the odd one out. You have forces that are perpendicular and you've got forces that are parallel to the incline. So instead, I'm going to replace that gravitational force with its components. All right. And please, when you draw a free body diagram, it's either you're going to draw the components of the force or you draw the actual, gravitational force. So I'm going to draw the components, and I know I've got the perpendicular component of gravity. So this is Fg perpendicular. And I've got the parallel component of gravity, okay, which is Fg parallel. Now, please note that the parallel component always acts down the incline. Okay, so it doesn't matter if my incline is facing, the downhill is that way, so it means Fg parallel would be acting down the incline, and this time here's down the incline, there's my Fg parallel. Now, as I said, if you had not watched my previous videos, what I would normally do, okay, is that I would just simply make a calculation quickly for my Fg parallel. Of course, I know that already I'm going to need them. There's my normal force over there. So what's my Fg parallel value? Okay, they gave me the inclined plane, okay, the angle of elevation there. So it's always going to be mg, the sine of angle theta. And now, please, ladies and gents, the only time we use that angle there is for the calculation of the parallel and the perpendicular components. Okay, so I'm not answering any question now. We've finished answering the one for the free body diagram. Okay, and by the way, these would be 1 mark, both of them together, or you can draw that one just alone. Okay, right, now quickly, right, let me just make an adjustment there again. Right, sorry about that. Okay, so in this case, now I know that my mass, the mass of the car, is 700 times 9.8, the sine of 30 degrees. Remember, we said we use that that angle of elevation there as, just for Fg parallel and Fg perpendicular. So that would be 700 times 9.8, the sine of 30. Okay, so that's 3430. Okay, that's Fg parallel value. Okay, so that's 3430 newtons. Okay, and then please, if you don't mind, I'm just going to put this on the side here and then continue over the other side. Right, now I'm also going to calculate the value for the perpendicular component of gravity. So I'm just going to say, well, my Fg perpendicular is mg, the cos of theta. If you really want to understand where this comes from, please, as I said, watch that video and you should be sorted, right? Okay, so in this case, we simply are saying this is 700 times 9.8. This is the cos of 30, okay? So our 700 times 9.8, the cos of 30 degrees. Okay, and we have 5940. Okay, 0.93. All right, I'm just going to round it off there. Okay, newtons. All right, that's our perpendicular component of gravity. Now note, it's this guy over here. Okay, now let's continue with the questions. I'm sure you're wondering, but what is he doing now? He's no longer answering the questions. Yes, we're getting to that. All right, now they say to us the car now starts from rest. So they're telling us it starts from rest at the base of the slope. Okay, so which means at that point over there. Okay, so we know the initial velocity is 0 over there and accelerates up the incline. Okay, they say the car's engine. All right, so now they overtly tell us that the engine is actually exerting a force. So they said it's exerting a force of 6,000 newtons, and the coefficient of kinetic friction between the wheels of the car and the surface is 0.32. Note what they are doing now. They're saying state the work energy theorem in words. What are they actually doing? They're actually telling you you might have to use the work energy theorem, right? Okay, so in this case, we know that net work done on an object is equal to the change in kinetic energy. You guys have a tendency of forgetting that change part, right? It's equal to the change in kinetic energy, or in this case, you can say the work done by the net force is equal to the change in kinetic energy. Okay, right. All right, now let's get into the next question. It's 8 marks. Hey, ladies and gents, look at how we're going to score ourselves an easy 8 marks. So that's 5.3.2. Now they say use energy principles to calculate the magnitude of the velocity of the car after moving a distance of 70 newtons. So now, please note, that's why we had to do Newton's laws, where we learned how to draw that free body diagram, right? So we know we are looking for the velocity when it gets at a distance of 70 meters rather. Okay, so what we are going to do, please, I'm just going to put it there so that we can track what we're doing. Okay, we're saying, all right, we're going to use the work energy theorem. So we say, well, the net work done on an object is equal to the change in kinetic energy. Okay, right, I see this pen just wants to give up on us. All right, we're not going to give up on it, but let's change it. Okay, right, now I want you to please note, we know that the net work done is equal to the change in kinetic energy. But now, how do we get the net work done, right? We can say, well, it's going to be the net force multiplied by that distance over there, multiplied by the cos of theta, is equal to the change in kinetic energy. So that's going to be kinetic energy final minus kinetic energy initial. Okay, so I know in this case that I'm going to have to use, because they've given me all of those forces, right? I've got that applied force, and so that's why I went this route. There's nothing about work done that they've given us, so I'm going to have to find that net work done using the forces. So now let's quickly do that. So what is my net force in this case? Now please note, remember, my net force, I'm looking at the forces that are acting in this particular case, right? I'm just going to do this. I'm just going to calculate that force, that net force over there. Okay, I'm just going to do it over here so that you can follow on. So what is my net force? It's going to be the force applied. Okay, there's our force applied over there. All right, so I'm taking direction going up. Remember, when it comes to work, energy, and power, please always take direction of motion as positive. Okay, so in this case, it's going to be my force applied minus the frictional force. Can you see kinetic friction over there? Minus Fg parallel. Why? Because it's opposing the motion, isn't it? Okay, and aren't we in luck? Because we've got the applied force, it's 6,000 newtons. Okay, minus, now you notice we don't have frictional force, but remember, how do we calculate friction? They gave us the coefficient of kinetic friction, right? So we're going to say, how do we calculate friction? We know frictional force is going to be the coefficient rather, multiplied by the normal force. But look, what's our normal force value? So you'll see that the normal force is actually at equilibrium with that FG parallel over there. Okay, so we can find that normal force. We know that the normal force would be FG perpendicular, but hey, look at that, we already calculated that over there, right? So we can say, well, if we wanted to find friction, we can say this is 0.32 multiplied by that normal force value over there. Okay, so what I'm simply going to do, fortunately I still have it in my calculator exactly as it was. Okay, so I'm just going to take that normal force value and multiply by 0.32. So 0.32 multiplied by our answer, and I get a value of 1901. Okay, you can please verify that for me, okay, lest you guys accuse me again of missing something. Okay, let's say 0.1. Okay, so I'll say 0.1 and then minus the FG parallel value, and remember we calculated that over there. Okay, that's 34, so that's minus 3430. Okay, right, now I'm deliberately leaving it so that you calculate it. So we've got 6,000. Okay, so we've got 6,000 minus that 190 something value. Okay, so it's calculated 3430 rather 30.1. Okay, and that's okay, so I get a value. Okay, let me just verify it. Right, I get a value of 668.9. Okay, so that's 668.9 newtons. Okay, and I get that value to be positive. So what does that tell me? It tells me that my net force should be in my positive direction. Okay, so I'm just going to simply substitute it there. So that's 668.9 multiplied by, remember they told us that this car moves up 70 meters there, so that's multiplied by 70. The cos, now note please, ladies and gents, which angle are we going to use there? Definitely not the 30-degree angle, right? We always said it's the angle between direction of motion and the force in question, right? So in this case, where is our where's our our net force going? It's going up the incline. Where's the direction of motion? It's up the incline as well. So what angle do they make together? Applied force, rather the net force going up the incline, as well as the direction of motion going up the incline. So ultimately you get that angle to be 0. Okay, right, please. And if you don't understand this, it means you haven't watched my video on work, energy and power. Please, I recommend that you highly recommend that you go and watch that video. All right, so we want the velocity up there, so this is going to be half times the mass of the car is 700. All right, and we want VF squared. Okay, and what's our initial velocity? Remember that they said the car moves from rest, so it means that our initial velocity should be 0 over there. We are almost there. Okay, so all that we need to do, some mathematical gymnastics. Okay, so I'm going to say multiplied by 70. Okay, and in this case I get an answer there, 46823. Okay, which is the product over there, and then divide that by 350, which is a half of 700. Okay, and I take the square root of my answer and I get 11.57. Okay, so VF is going to be 11.57 meters per second. And I hope that you understood that question. All right, just a little bit of a we had to do some work, okay? But in this case, I know that you probably will enjoy that, okay? Right, so please, if you haven't subscribed, please make sure that you do the right thing. And by the way, guys, it's very important. Please continue to work hard. Do those past exam questions. And if you guys encounter any challenges, you're more than welcome to shout on the comments, and also just hit that like button as well. Okay, right. And by the way, as I said, finally, for those of you that are interested in getting tuition or getting tutorship, right, on either physics or maths, you are more than welcome to get in touch with us. I'll leave the email address on my description below, okay, and also on the comment section. Thank you so much, guys. I'll see you guys next time. Keep working. Sharp, sharp.